Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about docking and berthing in space. So let's dive deep into it. So first, what exactly we are talking about? We are talking about two space-capable vehicle making love together in space. Now, this could be temporary, like marriages, or it could be partially permanent. So here's the deal. If you attach on your own power, for example, ISS is a thing. It's there in space, and you are going to there and then attaching, that will be classified as docking. If you go there and stay there, and then ISS grabs your ass, that will be classified as berthing. Basically, Cygnus is berthed into ISS, while Dragon capsule Mark II docks. Mark 1 was also birthed like this. So this is far, let's call it risky, but it's super slow and does require you to have big good enough precision where you at least go into in the range of Canadarm and orient yourself in such a way that it can be grabbed. While docking, it's much higher risk because if you oops it, yeah, kaboom. So that's a very serious system. And be mindful, if a country or a nation wants to do something serious in space, they have to sort this technology out. Meaning, you do not have space technology. It does not matter whether you have one rocket or 1,000 rocket. Unless you have good command over basically rocket technology, basically docking in space, you don't really, you can't really expand beyond a certain point. And the best example for this is Saturn V. Now you're like, okay, Saturn V is one rocket. It has docking system in that because again, because of the aerodynamics, the rocket was like pointy side up. Issue was the lunar module was bigger than that, so we're like, okay, we go like this, then detach, go like this, pull it back. So, and again, all of that was done in low Earth orbit. So that's why it's one of the best example of docking. And not to mention, for return also they had to dock lunar command module and lunar lander. So it is a very serious thing that you must solve and sort out in order to do anything serious in space. And space station will not be possible without it. It's like, no, there is no space station concept without docking. So this is why we are focusing on it. Now, first step of action is alignment. You have to align yourself in 3 dimension, not only in XYZ, but also in rotation. So you really need to align yourself precisely. Now, one common misconception you might have is that it's weightless, like it does not matter how heavy it is. Well, yes, you are weightless, but you are not massless. You still have mass. And penalty of that mass is that momentum and inertia still apply. Meaning, if a 20-ton object going slow speed and it just goes wham into ISS, it's not like, oh, nothing hit me. No. It's a 20-ton object hit you. So it's a big deal. That's why all the docking sequence you see in real life, in real speed, it's generally they have to be slow like that. Because again, you might think, okay, what will happen? No, at best case scenario, you're going to bounce back because again, they have a lot of spring in the docking mechanism for this exact reason. And worst case scenario, you're both going to go boom. So you have to understand that inertia and momentum, you must be very good with those things. You must be able to calculate them precisely. Failure to do so is like, yeah, no, you did. So that's one thing. And it must be done as gently as possible. That's why you will see first Cygnus goes there, arm just grabs it very gently. It's like, okay, bro. Okay, so even though you can see the mechanism can act very fast, they generally do not drive it as fast as possible. So you have a stick there, and that stick gets grabbed by the ropes, in-ear ropes, like the rope grabs it and then pulls it up. And again, all of that step is done slowly, so your inertia is not never exceeding beyond a threshold. Because again, you might be like, okay, I have Cygnus craft and I'm just gonna yank it. Can you yank it? There's a problematic part. Yes, you can, because there is no gravity fighting against you. There is no atmospheric drag fighting against you. You will yank it, and then the problem will happen. It's like, how the heck you will slow it down? It's like, oops. So for this reason, we have learned the hard way that we should do this slowly as possible, as gently as possible. And that's the Canadarm system, berthing system. This is from Apollo era, where they're like, okay, the probe went inside, locked it, then pulled it taut. Everything is done in step by step, and they have to wait. They cannot be like, kutu, 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 kutu. It's not a machine, pew pew. You have to go, you have to let things settle out. You let a spring relax, so there is no harmful oscillation or worst case scenario bouncing back. And even in the international docking adapter, you have a secondary ring that comes out to grab you. So all the shocks does not directly transfer into the main frame of ISS. It just like wiggles it a bit, slows it down, dampens everything, then it slowly pulls it up. So all of these things have to be done very precisely. And again, we generally call it probe and drogue shoot, mostly done. This cannot be classified. This is more like a flower petal, but it's international, meaning if you really want to, you can download the PDF from NASA and read up how to make it. Again, it's available for public. And again, that was the idea of commercial resupply missions. Everybody has to master this technology. Again, I have linked the video 8 years ago when they were like, yeah, Boeing is going to do it, SpaceX is going to do it. I'm like, Boeing is not going to do it. So this is the alignment step. You must make sure you understand the momentum and inertia is still there. You must do it as slowly as possible and gentle as possible. You cannot go wabaya. So this is the alignment phase of it. Then you have to understand, because you are trying to create a airtight seal, be mindful, there is nothing absolutely gas tight in vacuum of space. You will leak. The idea is you should leak slowly enough where it's not an issue, meaning if your resupply is supposed to happen every 6 months, and if you're not resupplying, you have something bad going on, so you'll be like, okay, it should not leak high enough rate where it's like under 6 months I will have an issue. Ideally, we'll design it, if no reply supply mission happens in 1 year, it should start to reach a bothersome issue, not at 6 months, 1 year. So everything leaks. So whenever we are trying to make a docking system, we try our best to not be like constant source of leak. It has to be low enough where it's like, for our intensive purposes, it's non-affection. Basically it's a non-zero. So metal surfaces do not like this, because again, if you touch two metal surfaces in vacuum, they're gonna make permanent love. So exposed metal touching in high vacuum is what we call cold welding. Basically, if you do not have oxide layer, for example, most of the docking components are made out of aluminum. If you know anything about aluminum, you know for a fact that they have oxide coating. And again, that coating is done by the oxygen in the atmosphere. And even if you did not have that, you had some metal that did not react to it in that way, you will have nitrogen and oxygen. All of those will create a buffer layer. So even though you can make them touch, there is a lot of enough molecules trapped there that it's not a cold welding scenario. But if you go into high vacuum of space, there is enough exposed metal that can just like touch it. And what happens when you touch it at that level of purity, it jumps. Electrons can jump from one to another. It's like, it's not like welding. No. It's absolute. Like, look into electron microscope and the metal is like, I never had a joint here. This is not two pieces, this is one piece. Or if you really had dissimilar-ish kind of metal, electron jumping will be slow. So it will like the fusing process was not precise. So, and again, we do use this in basically wire welding on Earth also. So for example, you take two wire, you do not need vacuum for it. You need clever trick with pressure. So you'll clamp it on both sides and you go, you clamp it. So it will push things out. Now that's swarf, as they call it, or the flash. Flash will remove all the oxide layer and all the exposed part, and slowly you will start to make love into pure metal to pure metal. And then it becomes perfect. As in like so perfect that you can test with electricity, eddy currents, X-ray, it will look like a normal metal. So you have to understand. And if you mess this up, like for example, Galileo, this done. The high gain antenna got kaput because it welded itself. So metal must be treated to minimize this risk. What are options? You have a lot of options. First is coating, second is anodization, and then third, you must have dry lubrication. Space does not like the idea of having metal going like this, because if you are going like this, which again, that's why the latching mechanisms are so huge, you will move a little bit. If you do not have lubrication there is a good chance you might grind a small area and just touch metal to metal. So lubrication, dry lubrications are generally utilized for this. So even like oops scenario, worst case scenario, you should not have a welding, because again, those metal scenarios, they are ground very flat. If you have that flat of a metal touching that flat of metal in high vacuum without lubrication, and again, any physical insertion force was applied, there is a good chance you might create some small spot that is like this, welded. So fundamentally, it must be tested under pressure and vacuum. So again, if you want to do cold welding on Earth without pulling vacuum, you utilize pressure. These are quite older techniques, so to say. So metallurgy is quite crucial here. It's not just like, just put anything. No, you have to think it through, and you have to think through all steps. Basically, what happens if it grinds like this? What happens if latching has a lot of vibrations into it? All of those have to be simulated, analyzed, ideally tested in a vacuum chamber. Then you deploy it in space, because if it gets permanently locked, you have to have some other boom bolts to detach it. Then we come to the fluid and gas part. Again, once you have the latching and material sorted, making it like an air tunnel is the easy part. But you have to still transfer fluid and gases. Now, mechanism part, like the actual latching and delatching mechanism, those have improved drastically. Basically, what we were doing in Apollo era versus what we have right now, they have improved. Like international docking adapter is rather efficient, so to say. It's like I have learned through all the mistakes of the past, and it's a really good system. However, when it comes to fluid and gas transfer, that part is lagging, like genuinely lagging. However, gas is easy to transfer because, for example, let's say ISS has a nitrogen canister. That canister is 200 psi. Let's just go with that. And you went there to resupply it. What do you have to do? If 200 psi canister is depleted, that means it must be below 200 psi. Or that means you must carry little bit of excess. Let's say 210 psi in your tanks. Connect it and let it through pressure regulator, and that will be refilled. Done. Not that complex. Surprisingly easy to do. And again, even with small hoses, as long as you're not leaking, because be mindful, as you have higher pressure, it leaks more and you are exposed to the other vacuum. So differential is huge. So you will leak exponentially faster. So that part is hard. But as long as you have pressure differential to create or pumps or all that, not that difficult. Pipe size also does not need to be huge. So that's the good part. So that's how ISS gets oxygen and nitrogen. While they do have their onboard oxygen generator, aka electrolyzer, but again, they also get it from other sources. Nitrogen, again, nitrogen they do read from other sites. And now what about fuel transfer? This is part where America messed up, or NASA messed up. NASA and Roscosmos had a relationship. That relationship was like, we're going to take care of the propulsion. We got this. And they got this, but problem was they did not got this that well enough. For example, that's why they have the mechanism of fuel transfer. You do not hear fuel transfer with international docking adapter side. It can be done. Nobody has implemented it. ISS core is not implemented in that way. The core of ISS has propulsion on Russian side. That's why they keep saying whenever they have fight, it's like, we're not gonna reboost ISS. And that's why America was trying at one point. It's like, okay, let's build something that can brute force it. Ideally, Starliner should be able to do that, ideally, but again, that is kaput anyway. Dragon was not designed with that oomph, so it can't really do it. So what they do is basically they have two tanks, and these tanks are diaphragm tanks, meaning you have a tank and it has a diaphragm. That diaphragm has gas pressure on one side and fluid on the other side. It's an easy, dumb way of making sure that you do not have to worry about void or bubbles or things of that nature. Good, awesome. It's a bit inefficient, but it does work. And what they do basically, once ISS has gone through what we call a reboosting, these tanks would be depleted. The fluid will be gone, the gas would have expanded. The gas will have much lower pressure. So let's say it was 50 psi, it's now as like 35 psi. So now you come with a fresh tank of fuel, attach it. Attachment points are somewhere here, this part and this part. So you attach there and just like open the valve. Now you have higher pressure pushes on the bladder. The bladder pushes fuel and propellant, basically oxidizer and propellant on both other independent line, goes into the tanks, refuels it, and then you detach, go home. And be mindful, this system is a big enough limitation at this point in time that a lot of advanced concept cannot really be done unless we have like refueling like easy peasy. So at this point in time, because SpaceX made rocket easy enough, that people are like, hey, we should solve this now. We no longer have the limitation of rocket. Like, okay, so one company is trying this, and be mindful, a lot of companies are trying this. I like the design, and the image was available. It's like it has 3 systems, and this is the passive one. This will be in the small drone units that will go and collect space garbage, and this will be in the master unit. The master unit will just clamp to these things. One is for data and power, one is for oxidizer, one is for fuel, and ta-da. And be mindful, that's why people are like so skeptical of Starship. If you say that we can just transfer hundreds of tons of liquid propellant, which is cryogenic, that's like, press X for doubt, not SpaceX. So it is fundamentally a stressful thing to do. So if Starship pulls it off, again, I do expect them to pull it off, but I do not expect them to be without incident. It will be one of the biggest, most successful thing. And again, that has to be done. If humanity has to expand beyond a certain point, we have to solve this out. Like, this has to be so long ago where it's like, oh yeah, we got this. Like, we do not even know how to do this. It's just like, that's how obvious it is. Like, you do not think about where the electricity is being generated. You just turn your switch on. So that, the fluid and gas part sorted, fluid part not so much, but we do have some idea and some more idea being developed. Now we come to data and power. Now data, again, if you have sorted all these things, data and power is not that difficult. So we do need to transfer power and data, because again, when you had basically space shuttle was running on fuel cell, meaning they had a limited amount of power. They did not have solar panel back then. So issue was, it's like, okay, ISS is there. ISS should supposed to feed the power into space shuttle. So space shuttle should not drain its hydrogen reserves in order to, like, make power. So like, okay, leach power from ISS as long as you can. After that, again, we have abandoned that idea. Now everything has solar panels, more advanced solar panels, and we realized hydrogen was stupid. So we are like, okay, we do not have that issue. But thankfully, because of this, power transfer is very good in ISS. Like, you can dump some serious oomph from here to there. So NASA docking system, that is a subsection inside it, that puppy can send 120 volt DC at 26 amps. That's 3 kilowatt continuously A to B. Basically, if Dragon needs for something, the Dragon needs 3 kilowatt of power, it's like, I got you. I got you. Docking side is like, I got you, man. Like these sort of electrical connectors, they're like, I got you. Do not worry about it. And Canadarm, because again, it also has motors in its joint, it does need, and because it clumps together, it has this connectors for that exact reason. It's like it can leach enough power there. It's not an issue. And data wise, whenever you are connecting data, you have two parallel connection. One connection is primary, that is called command and control. That system is like very dumbed down, very robust, meaning like there is no oops. And then you have a bulk data connector. So that's how we do power and data. Power part is surprisingly well, sir. Again, because of space shuttle limitation, it was like surprisingly, like, we can power you, puppy. We got you. We got the power. And data wise, again, because USA does have a lot of private partnership, they did improve the data side. And the future plan for somewhere I have read in the NASA documentation that they are planning for fiber coupling. That could improve the speed. And again, because you do not have dust in space, that fiber coupling could be outside. On paper, it can be done. I do not know how viable it would be, but it can be done. And that will allow like 10, 20 Gbps per second. And this is the part where, Russia and America shines so differently, where it's like, Russian system, fuel, we got this. Data, 5 to 10 Mbps. America, fuel, we do not got this. What about data? Oh, Gbps. Not even joking, that's that gap, Mbps and Gbps. So this is the power and data part. Again, this is not the hard part. Hardest part right now is the liquid transfer, especially with cryogenic and making sure it does not go kaput. And again, all other things are sorted. Power and electronics, again, we had some good system built into it. And if you look into the International Docking Adapter documentation, which is available for public, you'll see they have designed a lot of empty, quote-unquote, vacation slots. And those slots can be utilized for extra power. So if you're like, okay, I want to dump 10 kilowatt, 20 kilowatt, 500 kilowatt, you can just extend it if you need to. But again, why would you need that much power in space? But if somebody's like for in space manufacturing, they have spare space, physical space, where it's like, we are not gonna put anything other than this place. And what's supposed to be that place? Either fluid transfer or power transfer. So this was my presentation on docking in space, basically getting married in space. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.